All right. Today let's look at doing CFD and FSI analysis in LS-Dyna for a multi-phase flow problem, where you basically have more than one fluid material. A typical example is, say, for example, I'm dropping a steel ball into water, or in this case, something that's much more viscous, and then I can actually look at the flow pressure. I can also, couple very easily to the structural solver for LS-Dyna. This is a continuation of my CFD stuff. I will do more of it this year. All right, so let's look at. I'm gonna have an example for this, which is what I'm gonna do. But let's look at some basic information first. Okay. All right. So what I like to do today is just go over some important information that I think I need to remember for how to introduce multiple fluid domains inside the same grid, and that is something that's something we'll have to do inside LS-Dyna, and we have to know how to do that properly. So I'll share the basic illustration, then I'll do the example model. So this video is going to be focused on actually doing that example problem for the most part. Okay, so how do you assign multiple fluid bodies? So for example, if I start with a geometry like this, so if you watch my other CFD video, basically everything here has to be a surface body, and that's what construct the overall grid. But over here in the center, what you have is essentially is the location where the fluid material starts. Before that, it's like air, for example. Okay, so how do you separate that out? The same thing as before, right? So we still have the top region, which is the top half, and it's going to be assigned to one part. So you need to do an ICFD part volume, which is for all of the surface that you see here. And then we need to do a ICFD part volume for the second half of that. This surface body, which is shared between the two, are both included into the keyword. What we also need to do is to do a mesh volume. The mesh volume doesn't include the surface area here, that surface body there. It just includes all of the boundaries for the entire fluid domain, because the mesh volume is what generates the grid. And what we need to do is to make sure we cover the entire outside surface, and that's what generates the mesh. The mesh is different from the volume. The volume is what defines the material within that volume. The mesh is what generates the grid. Okay, that's the biggest distinction we want to make. So in this case, we have to have two different part volume cards, because we're going to have two different material assigned to those. And then on top of that, we have to define an interface, right? So this red surface, right, which is in the center, is defined by this inter-F keyword here, mesh inter-F keyword here. This keyword is what is going to call the mesh volume and tell the mesh volume that the middle surface that's in red is going to be interface. This is the basic requirement, right? So when we want to do analysis with multiple fluid parts, we have to individually create the volume. We have to have a partition that's called by the mesh inter-F keyword, and we'll have to have only one mesh volume for this kind of problem. Okay, and that's how you can differentiate the multiple fluid domains, basically. Okay, and then what you can sort of see is that within the actual geometry, I can actually refine my mesh accordingly, and it's going to translate to the fluid mesh, because the mesh in CFD is automatically generated, right? And then let's look at the example. Okay, so if you paid attention to my previous video, right, you have seen this video before where I introduced a lot of the setup example. So watch that video if you haven't. If you have a question, I'm jumping basically through this pretty quickly, because I only want to show an example of how to do a multi-phase flow, because this is where the FSI problem becomes much more interesting, where we're trying to sort of see how the deformation of a fluid, say a very viscous fluid, changes the response to a structure through that fluid structural interaction analysis. Okay. All right, so let's take a look at this CAD file right here, right? This CAD file right here is what I've generated. Basically, I have a solid part, right? I have a solid part, then I have a bunch of surfaces which defines the domain that I'm trying to deal with. Okay, so I already introduced this, but I'm gonna do this from the very beginning, step by step, in this example. Okay, so I'm gonna drag out a geometry file. I'm gonna call this demo, and then I'm gonna go ahead and import. I'm gonna go ahead and import the part that we wanted to look at, which I believe is the ball head impact right here. Is this one right here. I'm gonna get into space clean. Alright, while that's happening, I'm gonna load up my prep examples on the other side. Alright, give it a second, let it load up. Okay, now what we have is here. So in this case, what we need to do is number one, we're gonna hide the solid body, and we'll have a bunch of surfaces, right? What we wanted to make sure, number one, just to share topology all of the surfaces, because we cannot have two nodes be coincident inside a CFD problem inside Dyna, so we have to make sure we merge all of the edges. And this is where all the basic preparation for the geometry matters, is that you want to make sure you create a watertight geometry, right? And that's that. And I'm gonna hide this. So now I have a solid body in the same location as my wall, as my surfaces, and that's where the FSI interface is gonna translate. Okay. All right. I'm gonna get out of there, and then let's go ahead and drag out a couple Dyna models, right? So for CFD problem inside Dyna, we want to have a fluid part, and then we want to have a structural part, right? So we're gonna call this demo fluid. I'm gonna call this demo structure. All right, so let's go ahead and go in here. I kind of hate I have the load. Maybe I'll edit this part out, you know. Oh, I can enjoy the music. Okay. All right, and let's also open the structure side. Okay, while that thing is loading, let's look at this side. Okay, so on this side, what we have is a solid part. That you can sort of see there's a solid part here, right? And then what we have is a bunch of fluid parts, which are the surface body right here. Now, first thing, because this is the fluid side, I'm gonna go ahead and just suppress the solid side. And then I'm gonna assign some thickness and material. It doesn't really matter what I assign here. It's irrelevant, basically. I'll hide the contact. What I need to do before I even mesh it is I want to go ahead and set some termination time. That also doesn't matter. And I want to set the unit system to MKS, just because I'm going to write out the keyword in MKS. Okay, and then what I want to do here, right, the most important step is I want to go ahead and omit this and make sure I split my input file. Because that's what I'm going to do to generate the CFD mesh, is to actually do it inside LS-Spread post. Therefore, I don't need it to do it inside Workbench LS-Dyna, right? But the process is actually extremely simple if you think about what's actually happening, right? So what we want to do here is let's go ahead and just take all of these and assign this, and then make sure this is actually a triangular element, right? And I can take this into linear triangle element. And then what I also want to do is to assign a sizing to all of these, and then call this, let's say, what do I want to use here? In the example I use about 5 millimeters. Okay. All right, I'm gonna get rid of this. So I have a triangle for all the body, then I assign a sizing for all of the body. Okay. Now what I want to do next is that, you know, because I want to make sure there's a fine enough mesh around my ball, because that's the FSI, that's a fluid interface where the fluid is going to be contacting with the wall, right? So we want to make sure here is that we have a very fine mesh. Let's like do 0.5, and we also want to add a coordinate system at the center of this. And then what that's going to allow us to do is basically create a sphere of influence for this body, and then assign it to this coordinate system. And then I'm going to set a radius to like, let's say 10, right? And then let's define this to be also 0.5. So what this allows us to do is basically create two different mesh refinement. One is at here, 0.5. One is at here, right? And I'm going to mesh this. So now it gives me a very fine mesh across the center where the ball is going to be contacting. And then what this is going to happen is that it's actually gonna when you generate the volume mesh, it's actually going to follow the surface mesh and add a growth ratio to it. And that's where we're going to do this. Okay. Now because I already separated out my input file, I'm going to write this out. I call this ICFD demo. I'll call this fluid temp. Okay. Now if I go to my ICFD fluid demo, right, you can see I have a bunch of files that's already being generated. The one that I care about is the mesh card. Okay. So let's go ahead and open up LS Prep Post. And I'm gonna drop my mesh file in here. Now you see in my mesh file, this is the LS Prep. This is the mesh file that's loaded into LS Prep Post. Remember, I only loaded the mesh file, right? The mesh file has nothing except the mesh and the nodes and the mesh. It doesn't have anything else inside here. Okay, so this is the only thing I'm loading. But inside here, what we're gonna do here, we're gonna go to mesh. We're gonna go to MS mesh, and then this is where you convert the structural mesh into a fluid mesh, right? So what we do here is let's go ahead and assign the units here to do 90001 as my starting point, right? Like we just renumbers everything, and I'm gonna apply. Oh, I'm sorry, I need to actually select whole first. I'm gonna apply, and then reject, and I'm sorry, and accept, and done. And then what you have now, you have 1, 2, 3, 4, 5. These 5 different layers of mesh. Okay. Now what we do here now is I'm gonna save this. I'm gonna call this the fluid mesh. Okay. Okay. And what that's gonna do is gonna generate a fluid a new keyword here called a fluid mesh. Right, so if I open a fluid mesh, you can sort of see all I have are these shell bodies. I have nothing else, right? And then I have my elements, then I have my nodes. That's all I got. But this makes it a CFD ready keyword. Now what goes on, what happens from here forward is that you can actually take this back to LS Prep Post to set up your model, or you can do what I'm about to do, which is I have a CFD setup template for basic problems. I mostly do CFD analysis in Dyna, mostly for FSI reasons, right? So the kind of thing I use is a keyword template that I can basically use and apply to everything, right? So I already have this prepared. Now I'll go over this as I do this, so that you can sort of see what I'm doing, okay? And I'll go over this one by one. And I already created sections for his. Okay, so in this case, what I want to do is that I have 2 different materials here, right? One is gonna be vacuum. The reason I know it's a vacuum is because the flag number here is 0. That basically makes it like a vacuum-like material. For my first material with the MID 1, what I wanted to do here is that to set the viscosity instead of 1000, which is what I had as a dump. I'm gonna do this 0.001, and that makes it approximately water, right? Water. So water is about 1000. Actually, this card actually is water too, but I'm just gonna use it here, okay? And you can look up the keyword yourself if you want to learn more about it. But basically, this is what I'm doing: is I have a keyword template that sets my section and my map material card. Now with this, what I'm gonna do down here is I'm gonna go ahead and assign each of these correctly. Now I have 0, 1, 2, 3, 4, 5 start with 9000, right? So if you look at this, if you look at here, it tells you what it is, right? So if you look at what I have, so this one is the fluid bottom, this one is the interface, this one is the top, and then if I delete these 2, what you have is that you have the ball, right? So 4 and 5 are the 2 half of the ball, 1, 3 are the outside, and then the 2 is in the center, right? So I can just rename it here. So this one will be the fluid outside, and this one is the vacuum outside. This one is the ball 1, and this one is the ball 2. Oops. Right, and then what I have here is the interface. Right, and then according to each of these, right, the fluid outside is gonna receive the material of the water. Interface is going to receive the material of water. The vacuum is going to receive the material of vacuum, and then so on. So are the 2 balls, right? That's how I properly assign the material. And the section for each of these is going to be 1. Right, there we go. Thank you, Copilot. All right, so I have these properly assigned, right? Now I can go back to my order. Let's go to the next section. All right. So now this is where I need to assign my volume, my ICFD volume, right? So the ICFD volume here, what you wanted to do is to look at the way the volume works. Remember in the presentations, right? I said the volume here is that you have two. This is the vacuum volume, and this is the fluid volume, right? So the fluid volume, if you look at the keyword in LS prep post, right? The fluid volume is basically this two, right? So 1 and 2 are the fluid volume. So what you do here inside the keyword editor is that you just go delete everything here. I'm gonna name this actually 8,000. Oh, sorry, 800,000, right? And this is the fluid volume. Therefore, I'm gonna assign material 1 to it. And then over here, I'm going to do 8001. And this is going to be the vacuum, right? Vacuum is going to be your 3 or 4 and 5, basically, right? Well, actually, you start 3, 4, 5, and 2, actually, and 9002. So, all right, so I can just do 3, 4, 5, and 2. Okay, so let's check. So 1 and 2. What is 1 and 2? 1 and 2 is these two surfaces right here. That's the fluid part. 3, 4, 5 are the outside, which is the vacuum part, but you also have to include the fluid part, the interface, which cover both the volume and the fluid, and that's the one you assign to the second mesh volume. Now, once you have the mesh volume, you have to generate a mesh, right? So you have your oh, I'm sorry, this is actually not the right input. My apologies. Silly me. I actually didn't do this right. Apologies. Yeah, so let's just correct this. So this is actually going to be 1, and this is actually going to be 2. Now the mesh volume is going to include everything except for 9001, right? So 9002 is going to be the interface. So the total mesh volume is going to include basically everything. This, and this. So these are all the body that you're going to include, which are 2 ball and two surfaces on the outside, which is going to be 1, 3, 4, and 5. 3, 4, and 5. Now, what we didn't include is the interface, right? Therefore, the interface has to go here. So I have to call the mesh ID and then add the interface here, which is 9001. Okay, if this is confusing, just remember from here, right? If this is confusing to you, it is pretty confusing, but that's the way you have to do it. Either you do it in code or you do it inside LS prep. It really doesn't matter. Some people like a visual, but stuff like this is simple enough that I don't have the visual. I can just sort of visualize in my head what's gonna happen. But basically, you have to define volume here, and then do a mesh volume across everything except for the interface, and then you're gonna have to add an interface, right? Which is the 4 things that we did, right? Mesh volume 1, mesh volume 2, power volume 1, power volume 2, mesh volume, and then the interface. Interface calls the mesh volume, adds the interface to it, and that's how you know you're doing this correctly. Okay. Now control mesh gives you a way to control the growth factor for the mesh itself. The mesh size itself, we don't need it in this case because that's a local refinement. I'll go ahead and suppress that. The BL here is important because we want to put the boundary layer along the ball, which is with ID 3 and 4, right? So I'm gonna go do this as 3 and 4. Now the actual number itself is interesting, right? The actual number itself you have to think about. There's a setting here that you can work with, but basically if you go 3 here, you can use basically a total layer, a first layer thickness, which is over here. I can add this as my first layer thickness to be 0.1, and then I can add my growth factor, which is 1.0 or 1.1, which growth outward if you want. And I can define how many layer of mesh I want. I can add 10. So these 4 number right here defines what is your total layer, what is the first layer thickness, what is your growth factor, how many layer do you have, and that logic is defined by the number 3. If you go to number 1 and 2, it's a slightly different logic, but it's a very different for the ANSYS measure, except this is done in code, right? So you have to look at the code and know what to do, and that's how you define the boundary layer for this case. Okay, now the free slip and the non-slip is easier to see, so you have to go back to LS prep post and think about what is a free slip. So free slip is going to be my 1 and 3 is going to be my free slip. My 4 and 5 is going to be my no slip because that's near the wall. There's no slip near the wall, but I'm going to have free slip near the outside, right? Okay, so in this case, I'm going to have 1 and 3 as my free slip, and then 4 and 5 as my no slip, and then my 2 is going to be my interface. So I don't touch that, right? My interface is not something I touch. Interface right here, right? Oh, I'm sorry. Interface is gonna be actually 9002, I believe, not 1. Yeah, sorry about that. Let me double check. Yeah, my interface is gonna be my 2, not my 1. Okay, yep, there you go. That looks about right. Okay, and then I don't have any boundary, I don't have any inlet outlet stuff here, so I don't need to worry about that. I don't need these curve either. And then I have my drag database, which I want to put on my wall, which is going to be my 3 and 4, right? And all this stuff, you know, if it seems complicated, because but you know, if I were to have, say for example, uh, if I were to have, if I were to have like this open and this open on my other screen, right, like this, you can sort of see what's going to happen in between them, right? Obviously, you have to make sure the screen is captured correctly, but there's a different way you can handle this. All right, the control FSI card, I'm going to handle this in the other side, so I'm going to suppress this, and the other one, I'm going to do this at over 0.01 seconds. And I want to make sure my DT is small enough. It's going to be like 0.001 because this is an impact problem. It's highly transient, right? And then I have everything else assigned. Okay, now this is my entire CFD. Okay, I just did everything inside code, right? If it seems confusing, it may be, but once you get used to it, it's actually really easy to do. It's really not that hard, even if you have a slightly bigger model. All you are doing is define the characteristic of each of the walls, right? So in this case, I have 5 walls. You just have to define the behavior of the 5 walls, and you have the correctly CFD model put together. Okay. All right, so let's look on the FEA side, right? On the FEA side, I'm gonna suppress all the CFD stuff to start. And all I have is a ball, right? Well, would you like to guess how easy it is for me to generate the work I wanted to do, right? So I can suppress this, and I'm gonna put a method here. Remember, I just want this thing to be a tetrahedron, just for simplicity reasons, right? And I can put like I think the mesh I used was 1. Okay, so let's just do 1 here, and I'm gonna mesh it. All right. Okay, and then what I'm gonna do here is add an initial velocity to here, and then I want this to be in the y-axis to, like, you know, 1 meter per second. I'm gonna make sure I change this unit system to MKS, and then do 0.01, same time step as the other one. Okay, now from here on out, it gets a slightly more involved, right? So on the FEA side, what we need to do is to make sure we set up this problem as an implicit analysis. The reason it has to be implicit is that for a strongly coupled problem in Dyna, you have to do this as an implicit analysis instead of an explicit analysis. Now I just copy paste a bunch of coding here. If you haven't followed these, look for a video in my YouTube channel for how to do implicit analysis. Basically, I have an implicit code template. My implicit code template handles the setup for implicit analysis relatively well, right? And that's basically how I I'm trying to look for my implicit database, my implicit code template. Yeah, right here. This is sort of my implicit template, right? So I just copy something similar over here. This implicit template basically allows you to handle, set up this problem as an implicit analysis, but basically I have the same time step as my fluid side. I'm making sure it's not automatic, and I just solve implicitly. It's actually really simple in this case. Okay, and then what I'm gonna do next is I'm gonna add FSI interface. I'm gonna call this is implicit control, and this is FSI. Right, the FSI stuff is only 2 different cards, right? So FSI basically will have to define FSI interface. So FSI interface in our world is gonna be, remember, it's gonna be your 4 and 5. Remember, your 4 and 5 is your ball, right? So in that keyword there, all I'm calling is the ID for these 2 fluid parts. And I need to make sure they're in the same location as my mechanical part, which I did because I was doing this inside SolidWorks first. I make sure they overlap each other. And here is how you define the FSI interface. If you set this to 0, you basically have a strongly coupled 2 FSI problem, which requires implicit solvers to initiate. Okay. And you know, believe it or not, that's basically it. And what I want to do next is let's go ahead and add an include card. Add an include card. This include card basically is gonna include the fluid mesh ID. You see this right here just includes the file that we were just modifying, right? And then from there, I need to generate a control card and a database card, which I usually do because I disabled them. So let's make sure we disable the standard control card, and make sure we disable the standard interface card. All right, and then over here I have my database. And I have my control. And then if you've watched my video, you know I have these standardized database cards that I use for all my problems, and I have a standardized control cards which I use for all my problems. These things I modify them as needed, as a needed basis, but this basically handles my problem really well. And in this case, I want to make sure my ID is actually pretty small, which is good. Okay, that's all I have to do, right? All I did was add a control card, a database card, a include file, then define my FSI, then I define my implicit control. And with that, this ball basically just dropped through air at 1 meter per second, right? But because the FSI interface, right, it's going to be able to handle the correct play demo. There we go. FSI ball. Okay. Okay. Now because of this, what you have is that now this play FSI ball right here, right, is going to basically handle all of the entire problem because the include file that existed is gonna call this file we're just creating, and it's gonna basically generate that initial velocity. And this right here is your FSI interface. This is your FSI control, which defines what kind of FSI you're doing, right? How do you detect the boundaries? Because they're overlapping each other, this is almost trivial to do. And then once you do all of this, all you have to do is just solve this FSI ball file, which includes the fluid mesh. And then what you have is, I'm not going to solve it here because I'm solving something else right now, but I have the results right here I can show you, right? Inside here, for example, I believe this is the more viscous example where I set the viscosity to 1000 instead of 0.001. So this is an extremely viscous fluid. But if I were to look at over here, right, what we do have is a situation in which they look like this. Okay, let me get rid of those sections. I don't need the section anymore. Okay, see here, and then what I'm gonna do here is that I'm going to I'm gonna make this a little bit. There we go. Looks better. Okay, then I'll play. Right. So what we have here is that the ball is gonna interface with the water, and you get this effect. It looks actually pretty real in my mind. This is only 1 meter per second. Remember, it's not a really high speed impact. I can probably do an even higher speed impact to see what that look like, but the fluid part and then my grid is gonna get too small for me to even do it with a student license. So that's probably the limit what I can do at home, right? But something like this looks pretty awesome. And what we can also look at is, we can also look at a cross section. Look at a cross section. Sorry, a cross section right here. And I can get rid of the ball. And now you'll see here is a wall that basically goes through like this. All right, looks awesome, doesn't it? All right, I hope this helps, right? This is how you look at a FSI problem in LS-Dyna with multiple or the multi-phase fluid. We can do this for any combination of fluid, really. It's a basic, it's a very, very basic multi-phase problem. Basically, I can define multiple fluids in the same domain and do FSI analysis. All right, thank you very much.